Hello. Today we're going to cover the combined law. What does that combined law mean? It means that if you take Boyle's, Charles, and Gay-Lussac's law and squeeze them all together, will the relationships still hold up? In other words, can you change three variables instead of two variables? And the answer is yes. Notice we are still holding the number of moles constant. So we're still dealing with sealed containers of gases here. So if you take a look, the numerator of the ideal gas law, if you hold temperature constant, then you wouldn't use the temperature. And so that would be Boyle's law component of it. And if you held pressure constant, so it wouldn't be a factor, then you would get Charles' law. And this is actually how I teach it in my ICP class. We don't go to the individual laws. We teach the combined law, but then we talk about if you hold it constant, you just mark it out. And then, of course, the final law, if you have volume being held constant, then you have Gay-Lussac's law. And so that's how that works. Combined gas law problems. So you're actually asked to go ahead and solve the combined gas law for V2, because that's a lot of times what you're after in these problems. And so let's take a look at how we would go about solving for this guy right here. Well, I would multiply both sides by T2 all over P2, so these guys would cancel. So I would take, T2 all over P2. And so V2 is equal to V1 times P1 all over P2 times T2 all over T1. And so that's how you would solve for it. Let's take a look at how we would not bother solving for a certain variable, but just going ahead and working in the proportion method. But you just want to be a little bit more careful because you've got two things in the numerator. The volume of a gas-filled balloon is 30 liters. At 313 Kelvin, the T goes down here, and it's already changed to Kelvin for me, and 153 kPa. So there's all of the ones. The second set of circumstances says STP. Remember, STP are numbers. STP was 1 atmosphere or 101.3 kilopascals or 760 millimeters of mercury. Since this is in kilopascals, I am going to choose the 101.3 kPa. I don't know my V2. And my T2 standard temperature would be 273 Kelvin, 0 degrees Celsius or 273 Kelvin. Now, what I'm going to do to solve this on my calculator is I am going to take 30 times 153 times 273 equals, and I get a really pretty good sized number, which I just took three pretty large numbers and multiplied them times each other. I am going to divide that number by the product of 101.3 times 313. And so I'm going to use parentheses to join these together. So I put parentheses, I use the times button, and then I use parentheses to close it up. So divided by parentheses 101.3 times 313 into my parentheses and push my equals button. And I get that the final volume would be 39.5 liters. Let's take a look at another problem. You have a gas at 155 kilopascals and 25 degrees Celsius, which is 298 Kelvin. I added 273 to get that. And 1 liter. I need that to equal 605 kilopascals times V2 over 125, which is going to be 398 Kelvin. So on my calculator, again, I'm going to be very careful how I do that. I'm going to take 155 times 1 times 398 divided by parentheses 298 times 605 in my parentheses equals, and I get 0.342 liters. And then my last problem, I have 5 liters of air at 107 kPa. And I got 3 SIGs working so far. I have 250 degrees Celsius, which I add 273 to that and get 523 Kelvin. And I am going to change, I want to know what the new pressure will be if I have a new volume of 7 liters and at 102 degrees Celsius, which would be 375 Kelvin. Oops, 375. So I'm going to take 107 times 5 times 375 divided by parentheses 523 times 7 in parentheses equals, and I get 54.8 kilopascals. And that's combined law problems.